Alright, so in this video, I'm gonna be explaining another important article with the title DLOW, Domain Flow for Adaptation and Generalization. This paper in 2019. In this work, we present the domain flow generation model to bridge two different domains by generating a continuous sequence of intermediate domains flowing from one domain to the other. The benefits of our DLOW model are twofold. First, it is able to transfer source images into different styles in the intermediate domains. The transferred images smoothly bridge the gap between source and target domains, thus easing the domain adaptation task. Second, when multiple target domains are provided for training, our DLOW model is also able to generate new styles of images that are unseen in the training data. We implement our DLOW model based on cycle GAN. A domainness variable is introduced to guide the model to generate the desired intermediate domain images. In the inference phase, a flow of various styles of images can be obtained by varying domainness variable. So this is an illustration of data flow generation. Traditional image translation methods directly map the image from the source domain to the target domain, while our DLOW model is able to produce a sequence of intermediate domain shifting from the source domain to the target domain. In the domain shift problem, we are given a source domain and target domain containing samples from two different distributions. In this work, we propose to address domain shift problem on image level. So we build our base model based on the state-of-the-art cycle GAN, which is proposed for unpaired image-to-image translation. Formally, the cycle GAN model learns two mappings between S and T, which transfers images from in S into style of T, and G, which acts in the inverse direction. We take the S to T direction as an example to explain cycle GAN. To transfer source images into the target style and also preserve the semantics, the cycle GAN employs an adversarial training module and a reconstruction module respectively. In particular, the adversarial training module is used to align the image distribution for two domains such that the style of mapped images matches the target domain. So it's just an adversarial training. The reconstruction module is to ensure the mapped image to preserve the semantic content of the original image. This is achieved by enforcing a cycle consistency loss that is able to recover X when being mapped back to the source style. So you see many possible paths connecting source and target domains, while the domain flow is the shortest one, which you see on the red line. There are multiple domains, the blue dashed line, keeping the expected relative distances to source and target domains. An intermediate domain is the point at the domain flow that keeps the right distances to two domains. Now, modeling intermediate domains. Let us denote an intermediate domain as M sub z, where z is just inside 0 and 1 interval, is a continuous variable which models the relatedness to source and target domains. We refer to z as the domainness of intermediate domain. When z is 0, the intermediate domain is identical to the source domain, and then when z is 1, it is a target domain. So by varying this z variable in the range, we thus obtain a sequence of intermediate domains that flow from S to T. There are many possible paths to connect the source and target domains. As shown in Figure 2, assuming there is a manifold of domains where a domain with given data distribution can be seen as a point residing at the manifold, we expect the domain flow to be the shortest geodesic path connecting S and T. Moreover, given any z, the distance from S to M should also be proportional to distance between S to T by the value of z. Denoting the data distribution, we expect that the ratio is z over 1 minus z, where the distance is a valid guidance measure over two distributions. Thus, generating an intermediate domain for given z becomes finding the point satisfying this equation, that is, closer to S and T, which leads to minimize this loss. So we introduce two discriminator, d sub s to distinguish M, and d sub t to distinguish M and T. Then the adversarial loss is just the standard loss for both of them. Then we use just a linear combination of them from GST ds, GST dt. And then again here, cycle consistency, you can see that. But the total loss is a sum of the cycle consistency loss and the adversarial loss. So this is an illustration of boosting domain adaptation model with DLOW model. That's why it's a framework. We have this domainness variable z that I said it's just between 0 and 1. And after the discriminator provides the adversarial loss. Also, we have segmentation loss. But then they talk about this style generalization. For example, we have k target domains. The domainness variable then is just a km dimensional vector, but the sum of them is equal to 1. For example, z equal to 1 is a target, this is source, so anything between is just, that is, for example, this is a manifold, we are walking from the source to the target. So anything is between is, but we keep the shortest distance, the geodesic on the manifold, not any path. Otherwise, there are millions of paths connecting source and target.